Okay then, so this is a video to explain how to do some stuff related to physics using these categories of smooth spaces. So here's one thing that we can do. Let's say we have like a ball flying through space. So there's going to be a map from a location in the ball and a time to a space, okay? So giving us, for example, where a particular bit of the ball is at a given time, what place in space that's going to be. Now, yeah, we want to idealize these things. So, yeah, we'll look at a sort of simpler situation. Let's just start with the idea of a particle. So we'll have B as a point, okay? So there's only sort of one particle, let's say. And we're interested, let's say, in calculating the kinetic energy of that ball, of that particle. So that's given by the formula half of the mass of the ball times the velocity of the ball squared. Okay, so just for simplicity, let's suppose that our space is basically the smooth line and time is the smooth line. So s to the power of t is basically just r to the power of r, the space of maps from the smooth line to itself. And then we have the idea of differentiation, right? Because, I mean, basically our situation is a bit like this. We have s to the power of t, that's the space of trajectories, if you like, and we want to differentiate a given trajectory. So we want to send it to, I'll call it s dash to the power of t. Simple because the units are different, okay? Space, maybe it has units in meters or something, so s dash would have units of, say, meters per second, because a number in s dash is representing a velocity, okay? So we really just want the idea of differentiation. So let's just recall how this works. So we can think that there's basically a map, I'll call it D for derivative, from r to the power of r to r to the power of r. Basically, it takes one of these functions, one of these sort of points of r to the power of r, and it converts that into the function that gives the derivatives. So suppose we have a map f from r to r now, and then we can get f dash, which is also a map from r to r. And it's basically defined so that for any point x in r, if we form this function g of x from delta to r, which is defined so that gx of epsilon equals f of x plus epsilon for every epsilon in our, for every nil square infinitesimal epsilon. Then by our principle of microstraightness, we can find this unique b such that g of x of epsilon is g of x of 0 plus b of epsilon for all epsilon in delta. So I think one of my goals is going to be to formalize this stuff, okay? Maybe I'll have a little think about it now, so let's just make a bit of space. So here's R, and here's F as a map from R to R, and we also have delta here as a sub-object of R. So let's see if we can draw this another way. Here's R, and here's delta as a sub-object. Or maybe it's simpler than what I'm thinking of. Maybe not. Okay, I think it works like this, okay? So we've picked some point x of R. Whoops. I've got to think about this more, but we have another function here from R to R, and it basically takes the input and adds x to it. So we could, okay, let's see if we can write it properly. It's going to be plus of the input and x after exclamation mark R. Okay, so basically it's just the adding R function. And we also have, okay, let's call it this inclusion map from vanilla square infinitesimals. Okay, I got this the wrong way around. That's what I want to do, okay? So I think that this composition here is the G that I want, right? Because if we think about how this works on an epsilon, we've got f of plus 1r, comma, x, exclamation mark, r, on I of epsilon. Well, let's think of I as inclusion function, so it doesn't change the value, so this just works on epsilon, and then that's going to give f of epsilon plus x, and that's what we want gx of epsilon to be. So this is gx here. Okay, so that's fine. So then we get that, and then we have from the principle of differentiation this unique derivative b, and we define f dash of x to so given such a g, which is a map from delta to r, there's going to be a unique b such that gx of epsilon is gx of 0 plus b of epsilon for all epsilon as a nil square infinitesimal, and that b is the gradient of g of gx, and that's what we want. Okay, so now we can think about the velocity of our particle. So let's say it has a trajectory. Let's say that's given by this map k from time to space. Okay, and we're thinking of time and space of both smooth lines. So I don't have to put directional derivatives and whatnot in here for the moment. So then if we can think of the name of k, that's going to be a point of s to the power of t, and then we have this derivative function. So really this derivative function capital D that I've talked about up here, it goes from r to r, but all of this stuff is isomorphic to r, so I'm going to write it a bit differently. I'm going to say that D goes from the collection of maps from time to space to the collection of maps from time to s dash, where s dash is like space, but it has units of say meters per second. So I think this is kind of interesting because we have these sort of one-dimensional spaces, but they're associated with different units. So there's a question about how to encode that. Maybe one shouldn't encode that, but it seems like in physics, especially with things like addition, one wants to have quantities of similar dimensions to add them together. And so I imagine there ought to be a way of encoding this kind of stuff in category theory, but normally you just work up to isomorphism and you don't worry. So maybe one ought to put extra structure on these objects to reflect the dimensions they have. I'm not sure, but anyway. So then we want this map which gives velocity. Okay, so this is what I've cooked up. So basically, this map here is going to give a point of our space of maps from time to velocity, and so we just want to change that into an actual map. So we can just do it by basically doing the adjoint of it and then doing this isomorphism, and so we get this map V from time to velocity, and that's our velocity map. That's what we wanted. Now we want to get the square of a velocity. So we'll just say that this diagram commutes. We define this map V squared, and so we just take V comma V and then we use our multiplication. That's fine. We'll also suppose we have a point of R called a half, and then we just do the same trick again, kind of, to times V squared by a half, and then we'll also suppose we have a point of R called m, which is the mass of our particle, and we just do the same trick yet again. So we do the multiplication of V squared with m, we get half m. Sorry, we'll do the multiplication of half V squared with m, we get half mv squared, and that's indeed the kinetic energy that we wanted. So yeah, things to do: show that differentiation's a map. I've got to build more on the, I'm working on these videos explaining the foundations of synthetic differential geometry, the axioms Bell gives, and so on. We've got more video editing to do, and also there's a coverage of Brow's fixed point theorem in conceptual mathematics I need to work over.